Alright, this is going to be the first part of the final exam review. I will be focusing on Unit 6, which covers the moles and all those topics associated with the mole. To start with, the mole itself is basically a counting unit. It's similar to a dozen or a gallon or something of that nature. For chemistry, the mole is how we measure a unit. Avogadro was basically a dead white guy that said that 6.02 times 10 to the 23rd particles can be found in a mole. It's based on real calculations, but what you need to know is that 1 mole equals 6.2 times 10 to the 23rd particles. Again, this is a counting unit that we use to basically describe the amount of stuff in a substance. Now, we can use this relationship, 1 mole equals 6.02 times 10 to the 23rd particles, to convert between moles and particles. Now, don't forget that particles are going to be atoms, ions, molecules, anything of that nature. Alright? So this example. Zinc is used as a corrosive-resistant coating on iron and steel. It is also an essential trace element in your diet. Calculate the number of moles of zinc that contain 4.5 times 10 to the 23rd atoms. So here we go. We're going to take 4.5 times 10 to the 23rd atoms, and we're going to place it over 1. The reason why we do this is because that's the number we're given here. So you always, with these, you always start with the number. Let me go ahead and make this a little less busy. So we start with the number they gave us here, which is, again, 4.5 times 10 to the 23rd. We're going to use the relationship we just talked about. Because we have atoms here, we want them to cancel out, so we're going to place atoms on the bottom. The 6.02 times 10 to the 23rd always goes with the atoms here, okay? So that's going to go on the bottom, and we're going to put 1 mole on top. So essentially what we're going to do is we're going to divide the two numbers, and when we do that, you end up with about 7.5 moles. So this is going to help us convert between moles and particles. Now, molar mass deals with the mass of an element. Now, when we were talking about the periodic table last semester, we talked about some of the numbers they gave us. You have, let's say, helium. They give you the symbol in the middle, they give you the atomic number up top, but then they give you the mass down at the bottom. Okay, so this is what we're talking about in terms of molar mass. The molar mass is the amount of mass, or the amount of grams, that 1 mole of that substance has. And all of the mass on the periodic table are assumed to be grams per mole. So that's so many grams in 1 mole. And the number always goes with the grams. So, to calculate this, we basically simply add the masses of the different elements together. If we have multiples of one element, we'll multiply the mass by the number that we have. So, if we're going to calculate the molar mass of CCl4, which is carbon tetrachloride, what we're going to do is we're going to take the mass of carbon here, so this is the mass of carbon, and we're going to add it to 4 times the mass of chlorine. So here's your 4, because we have 4 of them. You multiply 4 times 35.45, and we add that to 12, and you end up with 153.81 grams per mole. So, to find the molar mass, you simply add the masses from the periodic table together, and you multiply by how many of each element you have. So in this case we have 4 chlorines, so we multiply the mass of chlorine by 4 and sum them all together. Now, we can use this molar mass to convert between the moles of a substance and its mass. So, the example, the characteristic odor of garlic is due to allyl sulfide. What is the mass of 2.5 moles of allyl sulfide? So the first thing we're going to do is the formula they gave us here is C3H52S. So we're going to take that and we're going to find the molar mass of it. So we take 6 times the mass of carbon, we're going to take 10 times the mass of hydrogen. Remember, this number on the outside here, you multiply it by what's in the parentheses. So it's 3 times 2, which gives us 6, and 2 times 5, which gives you 10. And then we're going to add that to the mass of sulfur. So when we do that, we get 114.22 grams per mole. So going back to the number they gave us, which is 2.5 moles, that's going to go up top here. And then we're going to put moles on the bottom. Again, we want to cancel out these units. So we always put the unit that we start with on the bottom of the next fraction. And the number here goes with the grams. So we put 144.22 grams on top. We multiply them, and in this case, you get 286 grams. So this is using the molar mass, which you just add all of the masses from the periodic table together to convert between moles and mass. Alright, now let's combine those previous two steps to go from particles to moles and then moles to mass. And we can go from particles to mass. The example they gave here, aluminum chloride is used in refining petroleum and manufacturing rubber and lubricants. A sample of aluminum chloride has a mass of 35.6 grams. How many molecules are present in this sample? Alright, since we're given mass, and that's the number we want to start with, we have to find molar mass. One thing I didn't mention about moles is that they are basically our universal currency. Everything is going to be converted to moles. We can't convert from gram to gram, but we can convert from moles to grams or moles to particles. So we have to first take this mass here and put it in moles, and to do that we need the molar mass. So we take the mass of aluminum here, and we're going to add it to 3 times the mass of chlorine because we have 3 chlorines. And when we do that, you get a mass of 133.33 grams per mole. So let's take the number they gave us, which is 35.6 grams. Grams is on top, so we're going to put grams on bottom. Again, that number goes with the grams. 1 mole is on top here. So moles on top here, mole will be on the bottom of the next fraction, and then we use Avogadro's number, 6.02 times 10 to the 23rd molecules. We just multiply and divide, and when we get that, once we do that, we get 1.6 times 10 to the 23rd molecules. So in this mass, 35.6 grams of aluminum chloride, you will have 1.6 times 10 to the 23rd molecules. Alright, one last thing as far as moles go is within a compound, we can look at the relationships between the overall compound and the amount of a specific element within that. And we can use that to convert between the moles of substance and the moles of its components. So in this case, we have aluminum oxide, which is Al2O3. It's the principal raw material in the production of aluminum. Determine the number of moles of aluminum, so this is just Al, in 1.25 moles of aluminum oxide. So we start with the number they gave us. So we're going to cross out, we want moles of aluminum oxide down the bottom. So we have 1 moles, because we have one of these, Al2O3. This actually should read 2. I will change that. So if we have 2 aluminums in our Al03, that will give us, let me recalculate this real quick because I can't compute, that will actually give us 2.5 moles of aluminum. Alright, I accidentally put in for 3. So aluminum actually has, there's 2 aluminums in aluminum oxide, so we multiply by 2 since we're looking at just the aluminum in there. So we can use the relationships of how many of the components or how many of the elements are in a compound to figure out how many moles of those elements do we have. Alright, so that wraps up the whole idea of the mole and converting between moles. Another thing another calculation we can do to help describe the composition of something besides moles is the percent composition. And we talked about this first semester with percent mass. Basically, again, this is just if you're going to do percent, it's the part over the whole. All right, so in this case, we're going to take the mass of an element, which would be your part. So this is a specific element over the molar mass of the compound, or the total mass of the compound. So that would be your whole. And you multiply by 100 to get into percentage. So this is a real simple calculation. Our example says baking soda is an active ingredient in some antacids and is used for the relief of indigestion. Determine the percent composition of oxygen. So we're just looking for oxygen in this case in baking soda, NaHCO3. All right. So the first thing we're going to do is we're going to find the molar mass, which we're going to take the mass of sodium, which is 23, plus the mass of hydrogen, plus the mass of carbon, plus 3 times the mass of oxygen. And when we do that, we get 84.02. Now this is going to be our whole, or our total. So that's going to go in the denominator. So that's going to go down here. Then we're going to figure out how much oxygen we have. Well, we're not just going to do one oxygen because we don't have just one. We have 3. So we're going to do 3 times oxygen here. So we're going to take 3 times oxygen, which I believe is 48. We're divided by 84, multiply by 100, and you end up with about 57% oxygen in this baking soda. Again, this is your part, which is your oxygen, over your whole, which is the total, and you multiply by 100. Now, the reason why we talk about percent composition, which leads into empirical formula. Essentially, what empirical formula is used for is if we find what the chemical makeup of a compound is by some means in the laboratory, we want to know what the formula is. And empirical formula is that formula we're going to find. It is the smallest whole number ratio of the elements. All right, it's basically our simplified version. It can't the numbers can't be divided any further. So like if we have C2O or something like that, that is going to be your simplified version. You can't divide the subscripts here anymore. Now, the process to do this is basically 4 steps. And there's a little rhyme here that we talked about in class. Hold on, let me clear the screen so that way it's a little bit easier to read. Alright, so what we're going to be looking at here is the little rhyme. It says percent to mass, mass to mole, divide by small, multiply to whole. So percent to mass is changing the percentages to grams. Mass to mole is converting from the grams to the moles. Divide by small is dividing by the smallest number of moles. And then multiply to whole is if we get a fraction, so if we get a 0.2, 0.5, something like that, we're going to multiply till we get whole numbers. So let's look at an example of how you're going to do this. So methyl acetate is a solvent commonly used in some paints, inks, and adhesives. Determine the empirical formula for methyl acetate, which contains 48.64% carbon, 8.16% hydrogen, and 43.2% oxygen. Alright, so the first thing we're going to do is we're going to convert all of those to grams. Okay? And what we're going to do when you do that is... hold on. So I don't actually show it here. I just went ahead and wrote it down. So here's our grams already switched from percentages. So the first step really here is percent to grams. All right, and I didn't write down the slide, but what you're going to do when you're doing that is you're going to assume 100 grams. All right, because if you multiply the percentages by 100, they just give you the percentages in grams. So we have 48.64 grams of carbon, 8.16 grams of hydrogen, and 43.2 grams of oxygen. Now, that's the first step. So percent to mass, or percent to grams. Then we're going to convert those grams to moles. Because essentially what we're going to do is we're going to compare the moles to one another. And this will give us our ratio that we want. So we take and we divide the carbon by the molar mass of carbon, which is 12.01, which will give us moles. And with these, remember when I mentioned earlier, you want to go out to about three decimal places, because the more numbers you have out there, the more accurate your answer is going to be. So we get 4.05 moles of carbon. We're going to take the hydrogen and divide by the molar mass of hydrogen, which is about 1, so we get 8.1 moles of hydrogen. And we're going to take the oxygen, the 43.2 grams, and we're going to divide by the mass of oxygen, which is 16, and you get 2.7 moles of oxygen. Now, that is the second step. So we've done percent to mass, mass to moles. All right, that's the little rhyme. This is actually mass here, and this is also supposed to be mass up here. All right. Now we look at our three values here, and this one here has the smallest number of moles, 2.7 compared to the other ones. So we're going to divide each one of these by 2.7. When you do this, you know you're doing correctly when at least one of your values for this third step will end up being 1. So oxygen will end up being 1 here. So we're then going to divide the carbon and the hydrogen by that, and we get 1.5 and 3. So these are whole numbers. There's not going to be any units because if you can see here, we're going to cancel out the moles. All right, and it's very important to keep track of which values go with which element. Now, here's what happens. So this is our divide by small in the little rhyme. All right, and if these were all whole numbers, so if this was 131, we would stop. However, we do have a decimal. We have a fraction. So what we need to do is we need to multiply by a number till they all become whole. So this is down here in the bottom. That's this is actually multiplied till whole. So let me erase this because apparently I can't write here. So we're going to multiply till whole. And if you have a half, the easiest thing to do is multiply by 2. So this will become 3, this will become 6, and this will become 2. So then our final formula here, and this is why it's important for you to keep track of which elements go with which numbers, are going to be C3H6O2. Okay, so once you get these numbers at the end, the last value, you just basically write them in formula. It doesn't really matter what order they go in. Typically carbon goes first, but you won't be docked points if you put hydrogen first or something else. Okay, so again, the process is percent to mass, mass to moles, divide by small, it's supposed to be a divide, multiply till whole. Often, if you get whole numbers in the divide by small, you stop. Sometimes you have to go on till the multiply till whole. All right. The empirical formula we can find from the composition of like composition data and stuff like that, but it's going to be the smallest ratio. The molecular formula is what you're more used to seeing. This is what the actual number of atoms that exist in nature, not the simplified version, just the actual value you have. All right, and the relationship between the two formulas is that the molecular formula is basically a multiple of the empirical formula. So this in here is going to be some sort of whole number multiple. So like 2, 3, 4, 5, 10, whatever. In order to figure out the molecular formula, you have to either figure out the empirical formula or you have to be told the empirical formula, and you also have to figure out, or you also have to be told the molar mass. Those two pieces of information you need to solve for the empirical formula. So let's look at the example. So succinic acid is a substance produced by lichens. It has an empirical formula of C2H3O2. Okay, so here's one piece of information we need, which is our empirical formula, and a molar mass of 118.1 grams per mole. There's our other bit of information. Now they want us to determine the molecular formula. What we have to do here is we have to first figure out the molar mass of the empirical formula, and then we have to divide that into the molar mass they gave us. We're going to get some sort of whole number ratio between the empirical formula molar mass and the actual molar mass. So here we go. Here's our here's our formula, the empirical formula, excuse me. So we're going to find the molar mass of that. So we have 2 carbons, we have 3 hydrogens, and we have 2 oxygens. So we multiply those by their masses off the periodic table. And when you add those together, you get 59.05. Okay? Again, the first thing we're going to do is find the molar mass of the empirical formula. Aha! This is not finished. Alrighty. So what we're going to do is we're going to go to a blank screen real quick. Alright, so we were told that, let's see here, 59 point, wrong screen. I do apologize. Let's see, white screen. Okay, so we had 59.05 grams per mole was our empirical molar mass. And this is, I will add this in. 118.1 grams per mole is our molecular. Molar mass. All right, so what we're going to do here is we're going to take 118.1 grams per mole, and we're going to divide it by our 59.05 grams per mole. And we're going to round to a whole number. So let me do that real quick, since this was not already done. And we're going to get 2. All right, so what we're going to do is we're going to take our original empirical formula. So this is the empirical formula they gave us, which is C2H3O2. And we're going to multiply the entire formula by 2. So that means what we're going to do is we're going to basically double all of the exponents. So we have C4H6O2. Now, this here is our answer. Okay, so you find the molar mass of your empirical, which we found to be 59.05 grams per mole. We divided that into the molar mass they gave us, which was 118.1 grams per mole, and we found a whole number ratio, which was 2. We then take that and we multiply it by the empirical formula, and that gives us our molecular formula. So again, our value is C4H6O2. Alright, last little bit that we're going to talk about with this unit is hydrates. Basically, hydrates are anything that has water attached to us. So you have, I don't know, let's say barium chloride. Okay, so we have our barium chloride. What's going to happen is this is going to be in a crystal structure. So let's assume this is your crystal. Alright, I can't really draw 3D objects really well. That looks really bad. But oh well, you get the idea. So that's a cube. Alright, what's going to happen in here is you're going to have your barium chlorides, your barium attached to chlorines. They're going to be in a structure. Amongst this structure is you're going to add in H2O. So H2O becomes part of the actual crystal structure. So this is why it's called a hydrate. The way that you write this, let's say that we have, I don't know, 3 waters per every molecule. It's going to be the compound, which is barium chloride, times however many water molecules you have. In this case, we have 3. So to name this compound, we name barium chloride, which we've already said, and then we use one of these prefixes. So in this case, it's 3, so it'd be trihydrate. So the name of this guy is barium chloride trihydrate. Okay, so it's the formula with a little dot and then the number of water molecules, and then to name it, you name the compound, and then we use these prefixes here on the right, plus hydrate. Now, one of the things we can do if we're given data from a lab, we can actually find the formula of a hydrate. And we have four steps to do that, excuse me. You find the amount of water lost, and you find the amount of anhydrous solid. So how much solid is left over once you evaporate all the water. The first thing you do once you find those two values is you convert the mass of water to moles. Then you convert the mass of the solid to moles. Again, we're going back to moles because moles is our universal currency. And then we're going to divide the two of those by each other. It's going to be the moles of water divided by the moles of solid. Okay? And you get some sort of whole number here. Let's look at an example. Alright, so our example here is a mass of 2.5 gram blue hydrated copper sulfate is placed in a crucible and heated. This is what we did in our lab. After heating, 1.59 grams of white anhydrous copper sulfate remains. So this is the mass here of your anhydrous solid. What is the formula and name of the hydrate? So, first thing let's do is let's go ahead and find our molar masses because we're going to need those values when we end up converting to moles. So, let's first find the molar mass of water. We take 2 hydrogens plus 1 oxygen and we get 18.02. Alright, by the end of all this review, you'll see me come up with this value a lot because it's a common compound we use. Alright, copper sulfate, we have 1 copper, 1 sulfur, and 4 oxygens. When we add all those together, you get 159.61. So we found our molar masses. We'll need those in a second. To find our water, we're going to subtract what we start with. So this is what we started with here. And we're going to subtract out the solid. So what's left over? And that will give us the amount of water lost. So we have 0.91 grams of water lost. So we take our grams, we divide by the molar mass here because we want that grams to cancel, and we end up with 0.05 moles of water. We do the same thing with the solid, so that 1.59 grams is our solid of copper sulfate. We divide by its molar mass, which we found to be 159.61, and we get 0.00996 moles of copper sulfate. Now, as I mentioned before, we're going to take our moles of water, which is 0.05, we're going to divide by 0.00996, and we're going to get 5. All right, what this means is that there's 5 moles of water to every 1 mole of CuSO4. So, when we write our formula, we write copper sulfate, which is our compound. The number that you find here in this dividing of the moles goes in front of the water. That's how many water molecules you have. So we have 5 water molecules, so we just put 5 H2O. Now don't forget that dot in the middle there because that's going to be important. Now to name it, we name the compound copper sulfate. We've already talked about that. And then we use, if we flip back a couple slides, okay, here 5 is penta. Okay, so let's go back to our example. It's going to be pentahydrate. Alright, that concludes this portion of the video for a review of Unit 6. Our next video will focus on Unit 7 and stoichiometry.